Okay, so good morning, or whatever time it is. This short video is going to explain part D of the assignment and the theoretical explanation of the MATLAB codes for digital modulation. So I've already provided you with the folder 4, which has a number of files in it. It has the introduction to comms file, which we've already talked about beginning. We've got theoretical values, so those are essentially, this is the code here, and the outputs for that file are here, which I will go through. These are the bit error rate curves. So when we send our signals across our channel, we have our additive white Gaussian noise channel, which is the simplest type of channel there is. We could simulate more complex channels, but then we would have a lot more errors. So what we do is we have our symbols. I'm just going to put 1, 0, 1, 1, 1, 0. They are transmitted across our radio channel. They are modulated here and demodulated here. So we would like to receive the same thing that was transmitted. So I've gone to my folder, Modeling and Simulation for Digital Modulation, and it contains MFSK, MPSK, and MQAM. We talked about that in the class. Now, these are all the folders, the files here that are contained in this folder. So, as I just mentioned, I'm going to go through each of these files in turn to show you what they mean. For speed, I can save my workspace. I don't know if you remember this, but at the moment, these values are in the workspace. If I say clear all, then they disappear in a second. When we're doing simulations in MATLAB, sometimes they can take a long time. So after we've done a simulation, we might save the variables. So I've done, for example, I'm just going to quickly jump into this one and say D1 QPSK additive white Gaussian noise. So this is the D1 file. So if I go to D1 and I've run that file once and saved the variables. So as in save the workspace and give them this name. So if this time, if I just double click on those variables, those are all loaded. Now I can miss out running the simulation and just run this bit and get the figures plotted. Just wait a second, which is a lot quicker than running the whole simulation again. They have appeared on my other screen. So I've got the bit error rate and symbol error rate for QPSK. Now the lines are the theoretical predictions. So when we talked about probability of error, for a particular modulation scheme, there is a probability that there are going to be so many errors. Now we talked about as we increase the M, the errors get larger for a certain EB over M0, so energy per bit per N0. We say energy per bit because we have in MPSK we might be sending multiple bits as a single symbol. That's why the bit error rate and the symbol error rate don't match exactly. Again, watch the previous video for a more explanation of that. And here we've got the crosses or the points, and these are the values that we've actually simulated. And what that's actually showing is that the simulated values are close to the predicted values. They're not always exact. As you can see, we've got above and below the curve. But what happens is the higher the value of EB over N0, so the signal power in relation to the noise power is much higher, then we need to transmit an awful lot of bits to get any errors. And for QPSK here, we can see that we have after 10 EBN0, then we don't have any more crosses. So that's because with the number of bits that we've transmitted, there have been no errors. So if we don't transmit enough bits, then these crosses won't be close to this line. Okay. So I'm going to close all my figures, and I'm going to clear all my variables. And I'm also going to use the command CLC so that my command window gets cleared. So we talked about the theoretical. So we have a bit error rate function, or the bit arguin function, which implements the theoretical equations. Sorry, my computer is slow. Shown by these equations that can be obtained from various sources on the web. Now, what this is that various telecommunications engineers, mathematicians have observed these signals and modulation schemes and defined these approximations. So what the point of today is, we're going to look at different types of modulation scheme and see how close they are to the predictions. So we start off with the first part of the A program, which, just zoom out a bit. The A program is generating the theoretical values for the different modulation schemes with different values of M. Now, remember that the M was the number of symbols. So 2 to the number of bits equals M. So 2 to the power of 1 equals 2. So that would be B, binary, phase, frequency, or FSK, PSK or FSK. Then if we had 2 to the 2, so 2 bits, that would be 4, or QPSK. I'm going to say PSK because it's, or FSK. Then 2 to the 3, which gives 8. We then just use 8 PSK. Or for general, MPSK. And these, obviously, the number of bits that are transmitted have to be an integer value. So it's 2 to the power of 4, 2 to the power of 5, so on and so forth, are the values that the M can take. So like I said, to speed things up, I've run these sections of code in the different programs A to E, and I've already printed or copied the plots. Now, I've shared this link in the assignments tab of the module, so you should be able to you've got a choice. You can run these yourself, or you can copy my images. So this program, we have EB to N naught 0 to 10. So we're going from 0 to 10 in steps of 1. M is 4, so it's QPSK or Q differential phase shift keying, and we're plotting FSK as well. So we use the function BER-AWGN, which you can look up in the help. We pass to it the signal to noise ratio, which is an array. We tell it what type of modulation scheme we want, and the value for M, which is 4 in this case, and for PSK it's non-differential, but for FSK, for differential phase shift keying, we don't have to put a choice of differential and non-differential, and FSK we can choose coherent or non-coherent. This is too much depth for this module, but I've just included that there for your if you want to go into this further. Above, so the lines above in this program do show you the different settings that we could have. Now I'm generating 3 curves: bit error rate Q for QPSK, bit error rate D, and bit error rate F. Now this Burr-Arguin, additive white Gaussian noise function, implements those equations that I gave you on the previous slide, which I talked about slightly earlier. So it's essentially a calculation. Send the values to a function. So I'm plotting this figure, which is a semi-log y, meaning it's got a logarithmic axis on the y-axis, and it has a normal axis or a linear axis along the x-axis. And I am plotting EB over N naught on the x, and then I've got 3 curves that I want on the y-axis: Burr Q, or QPSK, Burr D, and Burr F, and I do that by putting square brackets, and I label my axis in the usual way. Also the legend, QPSK, differential, and FSK. Now that's the actual program. However, what the important thing is how to read what that means. Now you will also be able to see these values. If I go to A and just run this, evaluate that section, you will be able to see the values in the workspace. So for the purposes of the video, I'm going to approximate them, but for you in your assignment, you may want to get the actual values. So I'm just showing you how to get the actual values by double-clicking on the workspace variable. It's just taking a little time to come up, and we've got the actual values there. You can copy these to Excel, but they give you 4 decimal points as standard, but if you copy them to Excel, it'll give you more decimal points because it's a double in size. So you can see from here that we have the 3 results, and Burr Q is 0.0786, 0.181 for FSK. So at a high noise power, QPSK is better than FSK, or QFSK, and better than differential phase shift keying. Now we can confirm that with our graph, that QPSK is the blue line, which is the lowest line, FSK is in the middle, and differential phase shift keying is the worst in this case. So if I just go back to here, if I draw, there's two ways of doing this. If I draw a line at a particular energy bit per noise level, I can read the values off at each curve and show that this is smaller. Remember, this is a logarithmic scale. So, and 10 to the naught is going to be 1. 10 to the minus 1 is 0.1. 10 to the minus 2 is 0.02. Up until 0.01. 0.1, 2, 3, 4, 5, 6. So that's how we read these curves. The reason that we put it on a logarithmic scale is because, well, you could try plotting it just using the plot command, is these values, you just would not see them because they would be so small. So that's the first bit of code in explanation. Oops. Then we are doing all different values of m. So I included a vector m, 4, 8, 16, 32, and 64. The reason that I started at 4 is because the theoretical values of 2 and 4 are the same. And also MQAM, we can only start. So for MQAM, it doesn't work for for one. We need 4 symbols for MQAM. So we can't have binary MQAM. We have to have, like, the m has to be 4 MQAM at least. So that's why I chose that. I go from 0 to 14, so I have a higher value, but in this time I go in steps of 2. That's just to reduce the simulation time. So we initialize all the variables. I'm doing it for FSK, PSK, and MQAM, and I do the calculation. I'm doing it this time in terms of a leap, which you don't necessarily need to understand the code for this. We just need to read the results. And I'm producing 4 figures. 1 figure for FSK, and this is the bit error rate of FSK, symbol error rate for FSK, and the same thing for the bit error rate theory for PSK, and bit error rate and symbol error rate for PSK. So I'm putting the grid on and the legends of all the numbers. So this investigation is showing the effect of increasing the value of m. I do that for MQAM also on figure 5, and on figure 7, 8, and 9, I compare the value between PSK. I plot PSK, FSK, and MQAM on a single axis for bit error rate. For m equals 4, so for 4, m equals 4 here, m equals 8 here, and m equals 16 there. I could choose any of the other values because I go up to m equals 64 just by changing this value and say m equals 64 and then just repeat this code. I can explain in more detail, but you don't need to know it here. But this just picks up a particular row of the variable. So if I then, it will take a little time to, oh, I could load the variables. So I've loaded my variables, and then I can go to this. I'll just plot these 3 figures. They're appearing on here. And I've forgotten to put the grid on because I like the grid. So if you want to, if the grid's not on in the program and you want to, I click on that one and just type grid on. Click on the next one. Now that one's got a grid. Click on the next figure. Do the up arrow for the grid on for that one. That one hasn't got grid at the moment. Same again. There we go, that one. Grid on. And now all my figures have grids. Figure 1. Sorry, that was figure 1 from before. Figure 7. Figure 8. And figure 9. Now, one thing to note is, as just looking at these quickly, you can see PSK, FSK, and MQAM. Now, for 4 modulation, we can note that I can't see a line for PSK. So there's no blue line there. But I'm sure it has values. What that means is it's got the same values as one of the others. So just by looking at that graph, I can't tell what that is. So if I look for bit error rate for PSK and FSK and FSK. So how to interpret this is we have big M is 4, 8, 16, 32, and 64. So the 4 values is the first column. The 8 values is second, 16, 32, 64. So 0.0786 for PSK is the same as MQAM, and PSK is higher. So I can then confirm, or I can copy these out, or I can plot just this line, and I will give you another WinZip file with these variables if that will help, but you could just simulate these yourself. So we have our figures, and we can see that PSK and MQAM performs exactly the same at M equals 4, with FSK being slightly worse. So if we increase M up to 8, then what do we notice? I'm going to make this larger. We notice that actually FSK is performing much better. So that goes down to 10 to the minus 16. So that's a very, very few errors. And we can see that PSK and MQAM are similar. However, at the, I can zoom in, but I'm not going to do it here, that the values for MQAM are slightly worse at 0 dB. However, when we come to a particular value, approximately 6, but you can be more accurate in measuring this, that they do cross over. And as the EB over N0 increases, the performance improvement is more significant. And then we'll look at m equals 16. Like I say, you could plot this for m equals 32 or 64, or any other 2 to the power of the number of bits. And we can see that FSK is still better, but these values are going much, much lower here, the bit error rate. So as compared to, no, not number figure 1, I'm just going to close that one down. Here we've got 10 to the minus 14, and FSK is actually not as good as the other two. Then we look at 8 modulation. It's now much better. I will show you in the next slide quickly. This is much better performance. However, its bandwidth is much, much wider than the other two. So as the M increases, yes, FSK does perform better than the others, but it takes up a lot more space in the bandwidth, which we know that when we're transmitting mobile signals, that's not a good thing. So here we've got in the order of 10 to the, it'll probably tell me if I hold on to it, 2.4, 10 to the minus 7, and here we've got 10 to the minus 6. So we can see that it's not doing as well. But there is a big improvement over PSK. So as the M increases, the performance does reduce. However, there is as the M increases, the difference between PSK and MQAM increases. So in my whiteboard, what I've done is I've drawn some lines. It's taken a little bit of time to go from one to the other because I'm using a lot of memory. So if you run the whole program, you come up. I'm going to concentrate on the bit error rates and not the symbol error rates. So for MFSK, we can see that as we said before, as the M increases, then the performance improves. However, the downside is its bandwidth does increase hugely. So we can see that the values at, say, 10 dB are improving as M is increasing. The opposite is true for phase shift keying. So as the M is increasing, so 4, 8, 16, 32, and 64, then the performance decreases. But this is much more efficient in terms of bandwidth requirements. So that's for phase shift keying. And then if we compare that to, because in your assignment you can comparing MPSK with MQAM. If we compare these values, we've got the same axis. So I just need to zoom out a little bit to get these two figures on the same screen. Could do with perhaps moving this legend, but if you measure, say, at 10 dB for both of these, then you can measure the values at, let's just take 64. So that's close to 10 to the minus 2 here, and at 64 it is more like 10 to the minus 1 at 8 PSK, we've got 10 to the minus 3. 8 PSK, it's, oh, sorry, 8 PSK, it's close to 10 to the minus 3. 8 QAM, it's closer to 10 to the minus 4. So we can measure those differences. So you can go into these variables and measure the difference. You can take them away from each other and report what the improvements are at different values of M. I would say choose a low value of M and then a high value of M and compare the performance difference between PSK and QAM. Now, that should be enough to cover, oh sorry, that will be enough to cover your assignment. But what I did also quickly want to show you, so you can finish it there. This is just the theoretical part. So you've got enough information in A for the assignment. B, this shows, oops, oh, this shows how the actual symbols are generated and sent across the channel and what it looks like when it has noise and when it doesn't. So this program, which is the B program, it is generating, this is just B, binary. We have a K log 2M is the number of bits, so that is the reverse of the equation 2 to the number of bits equals M. So if you place log 2 to the number of bits equals log 2 M, then we get the number of bits because those two cancel. So log 2 M. So I've just calculated the number of bits per symbol by setting the M value. The reason that I do that is because I do it in every single program, even the one that we've just done. We've generated a random integer between 0 and M to the minus 1. So M is 2, so we're going to generate zeros and ones. In this case, we're going to generate zeros, ones, twos, and threes. So the first graph, without going through the actual code, is this one. Is this one. I'm just plotting my data. So I'm plotting D, and I'm plotting. Let's do that. Plotting D, which is my input data. The number after M to the minus 1, the comma, that is how many data points. So that's 5,000, and it's a single array. So I've essentially got 5,000 ones and zeros. And you can run these lines in MATLAB to see that. Just do. Oh. I go to B and I'll just do this one for you. Go to the top, sorry. So I can see that D is 5,000, and if I double click on D, it is 5,000 long if you go down to the bottom. I'm just going to close because they don't exist anymore. And it is M. Then we have our modulated signal, which is next. So those are the values, zeros and ones, and Y is the PSK modulated signal. D is what we are modulating. We are having the value of M. That should really be M, but it's 2 for now, because M equals 2 anyway. I could replace that by a capital M. Remember, it is case sensitive. 0 is the phase offset. Sometimes it's useful to have a phase offset. Grey coded, and I am adding additive white Gaussian noise to our signal. So 30 dB and 0 dB. Like I say, you don't need to worry about this for your assignment, but this is if you're interested. So we have our symbols, input data. We've got 5,000 data points. They are either zeros and ones. They have a equal probability of being a 1 or a 0. Our modulated data, because it's PSK, is either a 1 or a -1, and they're all the same. When we have no noise, sorry, when we have a lot of noise, 0 dB, then you can see the received signal. So this is when we're actually transmitting the bits across the additive Gaussian noise channel. Then there is a lot of noise. So anything on the right-hand side or the negative side is deemed to be a -1 or a 0. And anything on the right-hand side is deemed to be a 1. We can see if we increase the noise to 30 dB, which is very high, that we do get 2 distinct areas of signal, and they're not exact as they are at the transmitted end, whereas there's only a small deviation of 0.1 and -0.1. I mentioned we could have a rotation. So if we say here PSK mod of pi by 4, which is possible, and we need to run those again, evaluate the section, then you can see that my signal has been rotated, and we could do by pi by. Also need to run from line 17 to 31 to do that, and then that will give us up there. So for the additive white Gaussian noise function, we just say the input signal, which is Y because it's being modulated, and then we add the noise plus the log. We need to add, to get the right theoretical value, as in to match the theoretical value, we need to match the value of M, and I'm not going to explain that here because that's too complex, but take this as correct. We could do the same thing for QPSK modulation. So now we have four values, 0 to 3, as I mentioned, and we have four distinct points. Here we've got a high value of noise, and here we've got a low value of noise. So you can see that it's going to be a lot easier to receive that signal. We do the same thing at, or I'm not going to do the same thing. I'm just going to, in this case, I have transmitted 5,000 bits, and I'm comparing, or I'm calculating my bit error rate, and my bit error rate, this 467 is the number of bits, so I can use the bit err function, and D is my input signal, PSK mod, Y is my modulated signal, Z is my received signal across the channel, and D estimated is the demodulation of Z. So once I've passed my signal through my channel, and my channel has 5 dBs of noise, then my bit error rate is 0.0331, 0311 even. So this is the actual simulation of sending bits across the channel and not just using those equations. So where I explained in the whiteboard here, where we've got D1, D2, and E. These are the actual values of simulated data for bit error rate and symbol error rate, and the red is the line of the theoretical expectation. You'll be doing that more if you do comms next year, but I know a lot of you are electrical. So that should be enough for your assignment. Okay, so MQAM is the same thing, but we have replaced the QPSK with the QAM mod and the QAM demod functions. So if I just run this, M in this case I've used is M equals 16. So we've got 16 symbols. So here we have our set of 4 figures. So we can see this time we've got 0 to 15 as our symbols, and they've been modulated nice and cleanly here. This is our modulated signal. I've not put titles on these figures due to time restrictions. However, you can add these if you're going to use any particular plots in your report. This is at, I assume, 30 dB, figure 3. So figure 3 is at figure 3 is at 0 dB, and figure 4 is at 30 dB. Because obviously I made the usual error of having the higher number as the larger amount of noise, but it's not the smaller amount of noise, and we can see really well that that is much closer to the transmitted values at the higher EB over N naught, even though it's not saying it on the axis. And that is that. I'm not going to go through the code in these. I will provide you with these variables so that you can run these simulate. So you've already got the code, so you can run the whole code yourself. But if I give you the variables, then you can just run the figures part. So thank you for listening, and that is all. And I hope that helps with your assignment.